Hey there, welcome back to Short Text 331. In this video, we're going to talk about eigensystems and inverses of matrices and linear operators in general. So recall that given eigenvectors v sub k and eigenvalues lambda k of some matrix A, we have by definition that A applied to its eigenvector is simply the corresponding eigenvalue times the eigenvector itself. And that is valid for the whole set of eigenvectors that comes with the matrix. Now we can assemble those eigenvectors into a matrix in this way in columns. So v1 is the first column, v2 is the second column, and so on, and vn is the last column. And so when you apply a matrix, the matrix A, to the matrix of eigenvectors, you obtain the same matrix of eigenvectors times a diagonal matrix made out of the eigenvalues. You might think, because of the way we usually write this top identity here, that the D should be to the left of V, but actually it's to the right. And you can convince yourself that that is the case just because of how we define matrix vector multiplication. It is that way, and also matrix multiplication, of course. So A times this matrix of eigenvectors then is the matrix of eigenvectors times the diagonal matrix that is made out of the eigenvalues, and it's a zero everywhere else. Now, if V sub k, the set of all the V sub k's, is a basis, in the space that we're living, in the space where this matrix hits vectors, then V inverse exists. So the inverse of this matrix exists if V sub k is a basis. That means that the columns are linearly independent, and so we're safe in the sense that there is an inverse that is well defined. And that means that we can go ahead and take this identity and apply V inverse on both sides on the right, and come up with this identity, which is nothing other than the spectral representation, which we found in a previous video. And that just tells us that any matrix A that has a complete set of eigenvectors can be written as the matrix of eigenvectors times the diagonal matrix of eigenvalues times the inverse of the matrix of eigenvectors. What's interesting, or one of the interesting things that results from this, is that you can see right away that the determinant of that matrix A is a determinant of this same product. It's just A written differently, but the determinant of the product is the product of determinants for square matrices, which is what we're looking at. And so that means that we get to split this determinant of this product into the determinant of each of the factors. And so we have determinant of V, determinant of D, and determinant of V inverse. Now the determinant of the inverse is the inverse of the determinant. You can convince yourself of that, and if not, we can prove that later. But that means that this factor cancels with this factor, because this one is the inverse of this guy. And so we're left with simply the determinant of D. And so the determinant of A is simply the determinant of the same matrix that we saw here that contains all the eigenvalues, which is diagonal. And so we get then the determinant of A is simply the product of all the eigenvalues. So lambda 1, lambda 2, all the way to lambda n. And so that's the conclusion of this first little bit, that the determinant of the matrix is the same as the product of its eigenvalues. And therefore we see right away that if all the eigenvalues are non-zero, then the determinant of A will be non-zero, and then the inverse exists. On the other hand, it's also true by the same token that if any of the eigenvalues happens to be zero, then this product will vanish and the determinant of A will be zero, and so the inverse would not exist. Moving on to a different point, we have this property that concerns the inverse of a product of matrices. So we're going into inverses now, and we ask the question, what is the inverse of the product of two matrices, M1, M2? Well, it turns out that the product, the inverse of a product is the product of the inverses, but in reverse order. And so the inverse of M1, M2 is M2 inverse times M1 inverse. And you can see, you can convince yourself that that's true right away, because if I multiply M2 inverse M1 inverse by M1 M2 like this, then the M1 inverse cancels this M1, I get the identity, and then I'm left with M2 inverse M2, which is the identity, and so that works out pretty well. And you can put this product on the other side as well, and then M2 would cancel first, and then M1 would cancel, and then you would end up with the identity once again. So in other words, this product, M2 inverse M1 inverse, functions exactly as it should, and so it is the inverse of M1 M2. And this generalizes to any product of matrices in this way. So the inverse of a whole product is the product of all the inverses, but in reverse order. And this is true for any number of matrices that you might be multiplying. And so this is interesting for us, because then to calculate the inverse of A, you can think of it as the inverse of this whole product, which we saw before. In other words, the inverse of A is the inverse of its spectral decomposition, which is V d V inverse. And now, so then we get to invert each matrix one at a time, but in reverse order. So first we put V inverse inverse, which is just V. Then we put D inverse, and then finally V, the first factor inverse. And so V inverse inverse is V, D inverse, and V inverse. And so this, in other words, is simply the spectral decomposition or the spectral representation of the inverse of A. And this is nothing other than a special case of an identity we saw before, which is that any function of A can be written as V times a function, the same function applied to the diagonal matrix of eigenvalues times the inverse of V, where here V is, of course, the matrix of eigenvectors, as we've been discussing so far. Now, we can take a closer look to a specific case where things are a little bit easier and which we'll use in the future and which is used a lot in physics. And that's the case where V inverse is V dagger. And so that's the case where V is a unitary matrix. And that's what happens naturally when A is normal. In fact, we saw in a previous video a theorem that told us that when A is normal, then that is equivalent. So this is if and only if. So it goes both ways. If A is normal, then it can be written in this spectral decomposed form that we saw up here, where V now happens to be unitary. And vice versa, if this V is unitary, then we can show that A itself is normal. And it follows also that these eigenvectors are orthonormal to each other. That's what we saw in a previous video. Now let's take a look here at what things look like when this V inverse happens to be then just V dagger. So the case where A is normal and V is unitary. And so then in that case, the element of V inverse, the elements of A inverse, element ij, is the sum from k equals 1 to n of V, the matrix V, element ik, lambda k inverse, V dagger kj. And all I'm doing here is simply taking this expression here and writing out explicitly all the indices of this matrix product. This is ik, k, and j. Normally, if you have two matrix products like you have here, you would need two sums. But here, because the matrix D is rather the inverse is diagonal, then we can do all of it with just one sum. You can convince yourselves that that is true. Now it turns out that this element ik of the matrix V is simply the vector k element I, and for V dagger we have something similar. It's simply vk star element j. And so then using that identity, using those these two identities, which are simply the descriptions of how we define the matrix V and the matrix V dagger, then we obtain that this A inverse element ij is simply the eigenvector of A element I, or rather the kth eigenvector of A element I, lambda k inverse, and then the element j of the kth eigenvector of A with the star, so complex conjugated. This is true for A inverse, but it was also true for A. Instead of lambda inverse, we just write lambda, and that gives us the element of Aij. This is again nothing other than the spectral decomposition of A itself. So let's look at an example of that that is interesting, because we can apply all this not just to matrices, but it turns out we can apply it to more general operators as well, like a differential operator. And this would be a case where n is infinity. Strictly speaking, we're going to be in an infinite dimensional space, but to fix ideas, this is useful, and to understand how things work in physics, because it works very much in the same way as in the finite dimensional case. So let's consider then A to be this operator, which is the negative, the second derivative with respect to x, and we're going to consider a space of functions that live on this segment 0 to L, and those are functions, those will be functions with these boundary conditions, that the functions in this space are going to be functions that vanish at 0 and they vanish at L. So if you want, this is like a hardcore box or hard wall box, and this could be then essentially the Schrödinger equation or a Hamiltonian of a free particle in a hard wall box, and whatever that means. If you haven't seen any quantum mechanics yet, that's okay. Just think about it in this way. So we have this operator, we have functions that satisfy these boundary conditions living in this space, and so this operator in that space of functions will have eigenvalues and eigenvectors. And so the eigenvalues and eigenvectors will satisfy then our defining equation for eigenvectors and eigenvalues. And the solution to this problem is simply the sine of k pi over L times x for the eigenvectors. This eigenvector is a function of x, and then the eigenvalues are simply k pi over L quantity squared. And it's easy to convince yourself that that works, because if you take two derivatives of this guy, then out of that comes 2 powers of this, k pi over L, and you get a minus sign also, because the sine becomes a cosine, and then when you take another derivative, it becomes a sine again, but with a minus sign, and so that takes care of that other sign here. And so you see that works out exactly as it should, and with eigenvalues given by k pi over L, which are quantized because this k takes on values 1, 2, and so on, all the way to infinity. And by the way, k equal to 0 is not allowed, because if you put k equal to 0, then this function vanishes entirely, and that's not a proper eigenvector. So eigenvectors cannot be vanishing functions. A vanishing function would trivially satisfy this equation, but it would not be interesting in any way. It's not what we want. So what is the spectral representation? Now that we have the eigenvectors and the eigenvalues, what is the spectral representation of A? And what about A inverse? That's interesting, because here, in these two expressions, we use the eigenvectors and the eigenvalues to decompose A and A inverse with lambda and with lambda inverse in a very nice way. But these are matrices. So how is this a matrix? So we're going to try to answer that next. So if we're going to write A in terms of this sum, something that looks like this, we're going to have two variables, x and x prime, in the same way as up here we have I and j, which is fine because we have an object with two indices, which is a matrix. But how would that work out in this way? How is A, the second derivative with a minus sign, a matrix? Well, the way to think about that and how that is true is that when we apply an operator to a function, what we're really doing is actually an integral. In the same way that when we apply a matrix to a vector, we're doing a sum over indices. Imagine if this were a matrix, this would be an index that we sum over if this were our vector. So, and this symbol, of course, means S is really a sum. So in reality, one should always be thinking about operators, linear operators applied to vectors in this way, as a kind of integral operator, which is characterized by this function of two variables. And this is our usual, what we usually think of as a matrix in conventional finite dimensional linear algebra. And to think about this operator in this as a derivative, then we try to rewrite the action of applying a derivative as an operator with two indices like this. And the way to do that is to use the so-called Dirac delta. So in our case, this x prime is a Dirac delta. It's a function that vanishes everywhere except when x is equal to x prime. Let's just leave it at that. And we'll see more on this later. And then multiply by this derivative operator, which is what we want. And so if we use this function defined in this way, if we use this definition, then we reproduce what we want, the delta of x minus x prime times the derivative of the function that we're looking at, the second derivative, with a minus sign. Then when we do the integral, this delta would saturate in the same way as a Kronecker delta saturates when x is equal to x prime. But instead of a sum, we have an integral, and this delta has this property that when you do this integral, then it collapses the x to the x prime, and we end up with exactly the result that we want. That A applied to a function is simply minus times the second derivative of the function in question. If this seems a bit like an esoteric object, don't worry about it. We'll come back to that in a future video that's going to be entirely about the Dirac delta. For now, just keep in mind that it has that effect that is very similar to the Kronecker delta, except that this one applies to integrals instead of sums. And it is this object, ax prime, that takes this form. The sum from k equals 1 to infinity of psi of k of x, lambda k, psi star k, a function of x prime. This is exactly the object that we need that would have the desired effect, and that has the decomposition that we want. In other words, this is really the matrix or the continuum version, if you want, of the matrix representation that we were talking about before. In the same way that we have this representation for our object ax prime with lambda, we have a representation for the inverse in this way. The inverse is a function of two indices, and now instead of lambda we put lambda inverse, And this actually turns out to be what people call a Green's function. It's a function that represents the inverse of the operator that we want to study. And we're going to see this in a future video as well, entirely about Green's functions. But this is our first encounter with Green's functions, which are simply the inverses of differential operators. Sometimes that fact is obscured by the fact that we don't often think of differential operators as integral operators with some function here that has this property. But that's the right way to think about this, and we learn to think about it in that way when we go into quantum mechanics, and this becomes absolutely necessary. An application of this is that when solving an equation of this form, where you apply an operator to a function phi that you want to know, and you obtain a result that's given to you. So this is a problem of solving for phi given rho. So it's a linear problem, in other words, with a given right-hand side. Then phi will be A inverse applied to rho. And how do we apply A inverse? Well, if we have the eigenvectors and the eigenvalues, then we can reconstruct this function A inverse of x prime, and we apply it as an integral operator in this way. So this is what one does. You go ahead and you do the integral over x prime of A inverse x prime. Rho of x prime is given to you. Now we put the variable x prime instead of x, but that's our right-hand side. It's information that we're given. And so now we replace in here, instead of this object, we put our expansion. The sum from k equals 1 to infinity, psi k of x, lambda k inverse, and I pushed through the integral to all the way to collect all the x-dependent stuff in here. So this object psi k star of x prime, rho of x prime, dx prime, and this doesn't know anything about x, and so it's just integrated over x prime. It's a function, it's a number that depends on k, so I called it b sub k. And in practice, if you need to solve a problem of this type, then what you do is, assuming again that you know the eigenvectors and the eigenvalues of the operator in question, you go ahead and you calculate this guy. You calculate this for as many as possible, or you use mathematical or some application that would allow you to calculate bk all the way to infinity, if possible, or as high as needed for the precision that you want. And this is something you can in principle do, because this rho of x prime is given to you. And this one you know. And so you calculate this, and then you form this combination, and you get your final answer, which is a function of x, which results from summing from k equals 1 to infinity, psi k of x, lambda k inverse, so the eigenvalue inverse, and this piece of k that you calculate separately. This is a very, very common approach to solving problems in E&M and beyond. And that's about all I have for you today. I hope you liked this video. If you did, please like and subscribe. If you're looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below. If you're interested in downloading the notes of this video, these notes that I'm showing here, you can find a link in the description below to my website, where you can download these notes and all the notes of all the videos. Until next time.